not known. So these were the main objects, along with, of course, the moon, which goes around here. So around Earth, we have our little satellite, goes around here. So that's our modern view, roughly. Then we have the sun in the middle and various planets going around the sun in elliptical paths, which are almost regular. And they're all essentially in a plane. Okay, they're all pretty well in a plane. And they're all going around pretty well in the sort of same kind of direction. So let's have a look at this a little bit more closely. This is what's happening to the Earth. Okay, so here we have the sun again. And over here is the planet Earth. And this is concentrated on this orbit. So it's going around. Here's Earth. And maybe I will put its north pole here, like this, and the equator here. It's actually somewhat tilted to the plane of this circular orbit. And it's going around like this. And so maybe the dominant thing is that the Earth revolves once around the sun in here. And it revolves or rotates once on its axis, axis in a day. Okay, so it's going around here, that's 855 point some years, some days rather, I don't know exactly. And at the same time, it's also spinning on its axis, and it goes around once a day. One day go around. And then we have the moon, and the moon is going around also more or less in a similar fashion. So there's the moon, and it's also going in this direction. And it goes around the Earth in well around 27.3 days or so. About 28 days. So it takes for the moon to go around the Earth. Okay, so let's have a look at this little model. So there is the sun, let's say, and here's the Earth. Okay, and you see I've drawn a red spot on the top of the Earth, that's the North Pole. And there's an equator there, and then you can see some of maybe that's you. Okay, although here I'm sorry we see down there, but alright. So here is let's say that we're having sort of look down on the situation, so we're looking down on the North Pole, more or less, of the Earth. So the Earth is rotating around the sun in this circular fashion, goes all the way around the sun in 1 year. And at the same time, it's spinning on its axis, and it's rotating this way, the same way that it's going around. So it's going around its axis like this, and it takes 1 day. So from there to there is 24 hours. And in that 24 hours, of course, it's gone a little bit along its yearly orbit around the sun. Now, things are a bit complicated because the Earth is not straight up and down like this. The North Pole is not directly tilting up in the plane of its orbit. It's actually tilted. Okay, so it's tilted like this. And this tilt is a very important thing. It's about 23 and a half degrees. Okay, so that's how far the North Pole's axis, the axis here, is tilted from the perpendicular axis of the plane in which it's moving. It's moving a plane. We'll see, make a table here if we don't want to. And then there's an angle here. Okay. And around this we have the moon. Let's say that's the moon. So the moon is also going around the Earth, and it's also going in the same kind of direction. So if we're looking down, all these directions are counterclockwise. The motion of the Earth around the sun, the rotation of the Earth on its axis, and the movement of the moon around the Earth are all going in this direction. Okay, so the moon is going around like this, so the Earth takes 1 day to go around like this. In that time, the moon has moved 1/30 of the way, 1/28 of the way around. Okay, so in 1 day, the moon will go from here to here. As the Earth goes around once, in 1 day, the moon goes around a little bit like this. And then we're a little bit further along the way around the whole thing. So these are the main features. The fact that we have more or less a stationary sun. We can see the sun stationary. The Earth is moving in these two kinds of fashions. And then we have this satellite moon. And then, of course, there are the other planets which are doing their thing. There's Mercury going around here, and Venus going around here, and Mars a little bit further out. And then way over there, there's Jupiter making a bigger circle, and Saturn making a bigger circle around it. Okay. And those planets, Mercury, Venus, Mars, Jupiter, and Saturn, are all visible to us with the naked eye. We can see them. And we can see them as bright light. And you'll notice that as we're moving along here, right, the plane of our rotation is also more or less the plane of which all these other planets are. So these planets are not up there. They're all more or less in this plane. Not quite, but more or less. So that means as we're looking, as we're looking in the night sky, then the planets are all likely to be along a relatively narrow band. Okay. Now, so there's these two kinds of movements. There's a revolution around the sun, there's a rotation around the axis, but there's also a third kind of movement, which is much more subtle. And that third movement is also coming from antiquity. It was actually discovered by Hipparchus, ancient Greek, probably the most prominent ancient Greek astronomer. And that's the precession of equinoxes. Okay, what that amounts to is that the Earth's axis is actually wobbling. It's much the same as the top. So you want to spin the top, right? So you get the top and you spin it like this, and it's spinning there like this. And eventually, maybe you hit the top, where it starts to make this kind of motion like this. At the same time that it's spinning very fast, its axis is actually wobbling. That's what people actually look at its axis. Imagine a spinning top. And at the same time as it's spinning, the axis is going around like that. Have you ever witnessed that? If I have a top spin it, and you'll see it, but it's not all straight up and down. They sort of start to wobble around. So what that means is that the Earth is doing the same kind of thing. That this axis that is 23 degrees from the sort of vertical of the plane here is actually itself making a rotational movement. So there's a further circle in this direction, which means that the North Pole, the direction of the North Pole, is actually changing. And how often does that change? Well, that takes about 26,000 years, or about 1 degree in 71 years. So that means that maybe at this period of time, here in the north, if you're tilted this way, that means this is the summer season, and then as you rotate around and you come over this side, then that's the winter season here in the northern hemisphere. So what that means is that in another 13,000 years, things will have changed. And when you're over here, the axis will actually be in this direction. And so the same place where the Earth is now, it will, instead of registering as being summertime, it will actually be wintertime. And that's very noticeable if you're watching the sky, because the constellations that are visible to you will change from different parts of the year. But if we're looking in this region here, we can be part of the rest of the night sky. After all, we're not just solar system. There's also other stars, which are many thousands of miles away in this kind of scale. But for these three stars, some of them are visible to us and some of them aren't. So if we're like this here, and things are like this, people who are on this side are experiencing nighttime because the sun is not visible to them. So this is the bright side, the daytime side, and this is the nighttime. So anybody over here will be looking out here and seeing those are the stars, the nighttime stars. So you're over here looking out and see all those stars, and that's the night sky. Okay? But when you're over here and the seasons have reversed, now, you're still there. Now the night time is the time that's shaded. So now the sun is lighting up this half, and this is the dark half. So now you're this evening and you go outside and you look out the night sky, you're looking at those stars. Okay. So you're seeing different kinds of stars than you do in the summertime. And over the 26,000 year period, those things will change. They'll interchange each other. So this was noticed, this potential equinox was noticed first by Greek geometer, 129 BC. And the reason how he noticed this, so he noticed this because he was comparing his records to earlier Babylonian records. Okay, so the Babylonians had been doing astronomy already for quite some time when the ancient Greeks came around. So even Hipparchus, who was a pioneer of astronomy, he had these earlier Babylonian tables to look at, and you can see that their descriptions of where various constellations were at various times of year was a little bit out from what he could observe. So we're talking about 1 degree every 71 years, so in 200 years it'll be 3 degrees, and you can start to measure that. So he noticed this by comparing his measurements with Babylonian ones. By the way, what is the wobble, this kind of wobble of recessional equinox is actually due to? So scientists these days understand it the following way, that the sphere of the Earth is actually not a perfect sphere. It's actually a little bit more bulging at the equator than at the poles. So it was a very good question back in the 17th, 18th century. They wanted to know whether the Earth was sort of flattened this way or flattened this way, whether it was more along the direction was a little bit wider. So there was a word controversy, and one stuff obviously about it. But actually it had scientific experiments go around the world to make various measurements to determine the actual nature of the Sport French expedition that resolved this question. And they found that, in fact, it was right, that the Earth was a little bit extended along the equatorial bulge. Okay, so this means there's a little equatorial bulge. It means that the sun's attractive force, the thing is like this, so the attractive force is not entirely uniform because they get the things are tilted like this, and that bulge down there is being attracted, and so there's a kind of a gravitational force that's wanting to push it this way. And also the moon also has a gravitational force that affects that bulge, so that's sort of the explanation in that direction. Okay, so we can see that the story is quite interesting, but this is really a modern point of view, right? This is a story that we now have as a consequence of all kinds of brilliant people's observations and theories and especially thousands of years of understanding, especially the Copernican revolution, which brought a heliocentric theory into the promise. Although I should mention that a heliocentric theory was not Copernicus' idea originally. There were Greek people who supported this. There was a fellow called Aristarchus, who had a heliocentric point of view. And in fact, there was also Babylonian astronomers who also had a heliocentric point of view towards what's going on. Okay, so that's all well and good. But now we have to come to what it was like for the actual ancient peoples. So the story is far from the way they would have understood it. Absolutely miles and miles away from the way they understood it. Okay, so we now have to almost forget what is contained in this picture and try to imagine what the world would have been like from the point of view of an ancient astronomer. So from an Earth-centric point of view, what actually do we see? Well, from an Earth-centric point of view, we are obviously stationary. Okay, you can see we're stationary. We can't feel anything moving. So the Earth is stationary. So here's some various observations that any sensible person would have made. The Earth is stationary. But the night sky rotates about it. Okay, and that's obvious. You just go out there and you have a look. You spend a few hours staring at the stars, and you'll see that that's exactly what happens. So you go out and you look at the night sky. We're talking about people who would have been a little bit these ancient civilizations, a lot of them in the northern hemisphere, not too far from the equator, but sort of middle latitudes, but still live in the northern hemisphere. Okay, so you go out in the night sky, you see the northern stars, and what do you see? Well, you get the night sky, you're looking at the night sky, and okay, there's all these constellations, some thoughts, so maybe here's some constellation that you think is a pair or something like that. It's just really a configuration of stars. And then you're watching that, and then you notice that a little while later, it's maybe a couple hours later, it's over here. It's moved. And the constellation that was over here has moved over here. And you can see, identify that there's maybe a star around there, which is more or less fixed. And so everything seems to be kind of rotating around this kind of direction. But what that secondly means is that this is sort of a big picture, but what I would have thought is that here's our Earth. Okay, here's Earth. And here is a sphere. What we deduce that the night sky rotates above it, and the stars are on a sphere. Stars are on what's called a celestial sphere. So there's a big sphere that's outside there, which is the night sky, and it's rotating. And the stars are fixed on this celestial sphere. The stars are on a celestial sphere which rotates. So here's the celestial sphere. And so maybe the North Pole is slightly straight up here, the North Pole is in this direction. So the North is in this direction. So there's kind of a rotation around this axis. This whole thing is rotating. I think that was sort of, as far as like, maybe there were some religious things that might have, might have guessed this or whatnot, beyond that sphere, but scientifically they didn't have any idea. Yes, so on the celestial sphere there are all these stars forming various constellations, and then there are these other things as well. Okay, common amongst them was the sun. So the sun is something else that's attached to the celestial sphere. It actually makes the same kind of movement as the stars do. If you watch all night long, you see the stars kind of coming up. They're coming up east and then coming up east and then going down to the west. Okay, so maybe here is there's north. Okay, so it's sort of going like this. And so stars are rising here, and then you can follow them all night long, and then around one time they pass the western horizon. And then around one time the sun comes up. In the same way, it makes the same kind of trajectory that the stars did, and at the end of the day, it goes down. And so you can observe that the sun is making the same kind of movement as the stars did. So the sun appears to be on the celestial sphere. And of course, the moon is also somewhere there. It's also making the same kind of trajectory. So there's the moon over here, and there's the sun, and eventually you realize that all these are planets like Mars and Jupiter. But the difference between the planets and the sun, the moon, and the stars is that the sun and the moon and the planets are actually moving on the celestial sphere. They're not in fixed positions. So we get a picture. So it looks more like this. They also introduced the Earth round. So all ancient astronomers basically do this. None of them thought the Earth was flat. No, the Earth is not. There's lots of evidence for that. I mean, if you have stars which are going, you see them going all night long, going like this, and then tomorrow they come up that way again. How's that possible? And obviously they're attached to a big sphere that goes around the there and comes, underneath us, and then around the outside. So obviously we're a sphere, and that celestial sphere is surrounding us. This one is spherical aspect of the Earth is found with the sailors. So when you're at sea and you're watching a ship sail away, it goes to the horizon. When it's on the other horizon, you see it sail, and then eventually its hull hits down. And you see the sail. It's not just the thing that gets beautiful and small. You see it with a flat thing. The top of the ship is visible, like the bottom of the ship is no longer visible. Same with an island. If you're approaching an island, you see the mountaintop of the island before you actually see the base of the mountain. That's the round. And the other evidence for that was in the lunar eclipse. When the Earth gets in the way of the sun's rays on the moon, you have a full moon, when the sun is shining directly on the moon, it's full, and the Earth happens to get in the way, there's a shadow, and it's obvious that shadow is round. You can see there's a round shadow that's directly to the moon, so the shadow here. You can see the shadow here. Here's the round. No, it's not what you talk about it. That's just something else. The latest knows nothing of science. I couldn't believe that they were that. So here's what the knew that, so it's here. And around the Earth is then this sphere. Okay, and so look at the sphere is rotating. Let's put the North Pole of the sphere here. Here's the Earth. And here's the celestial sphere. Okay, so that means we're having a celestial sphere. And that's why spherical geometry plays such an important role. But it's not a sphere that's not the important sphere. The important sphere is the actual sphere of the night sky. Okay, we know it's not actually a sphere, but it's really like a sphere. And you see why ancient people put a star in a sphere. So there's a sphere on which all the stars are rotating and the stars are fixed, and the sphere is rotating. And it rotates around once a day. And because there's a natural direction north, and it's like in the northern hemisphere, there's actually a star of the north star, which is almost exactly in that direction. So that's fixed on the rotation, so it's very easy to see where north is fixed. So then we have an equator. So the equator of this celestial sphere would be this great circle of this sphere, which is just perpendicular to the north direction. Now, there's also the sun and the other side. So here's another line, another great circle, and this is the path of the sun. So the thing of this whole sphere is rotating, yes, it's rotating around once a day. But if you take into consideration the sun itself is moving on this sphere, we know that because that's the case that we're actually moving around the sun over here. So we're facing the sun in a different direction with respect to the stars than it was over here. In fact, the opposite direction. Like this celestial sphere, the sun is that way, and over here, the sun is in that direction. So you're always pointing towards the sun as you're going around. The sun is out here. So you're actually wandering around this great circle, and that's what we call ecliptic. And that's like 23 degrees. And that really represents the plane in which we're traveling. So not just the sun is on this thing, but almost all of the other objects, the planets and the moon and so on, are in a relatively small band around the ecliptic. So around the ecliptic, there's the moon somewhere. Depending on what time of it is, there's the moon. And somewhere on the ecliptic are also Mars and Jupiter and the other planets. Five planets. So all the planets are basically on this ecliptic. Now, when they're moving on the ecliptic, because the sun goes around this thing once a year. The sun goes around once a year. More or less uniformly. Pretty well uniformly. Well, the moon is doing its thing, okay? It's going around once a month. So it's flowing more vigorously than the sun. The moon is changing its position from day to day. From day to day, you can see the moon is in a different position. As you can see, also, as well as the night sky. Every day, the moon is, maybe a degree, not 1 degree. So you get 60 divided by 27, so about 12 degrees further on than it was the night before. The moon comes up later and later, during the night. So the moon is doing its thing, but what's much more peculiar is the planets. So the sun and moon activity is regular, but the planets are more mysterious. In particular, the planets do strange things. We have to look at Mars. It's like, so Mars will be something like this, it will go in this direction, and then it will loop back for a little while, and then it will head back in this direction again. a strange thing. It's just the reason of trajectories. The planets are doing crazy things. And if you observe the planets night after night and you keep careful tables, and these ancient civilizations ended up doing that, they became very interested in where things were on a regular kind of basis. We kept tables, we kept track. Then you start to, kind of predict where things were at in times in the future. The planets are very hard to predict. The moon and the sun are, as we say, relatively regular. In fact, there's this important kind of regularity that happens. So the sun and the moon, they do something called a Saros cycle. So there's a Saros cycle of 18 years. So roughly every 18 years, relative positions of the moon, earth, and sun get back to where they started, and that makes predicting eclipses much easier. Okay, so we have these two great circles, but the story is not finished, because it's also us. We are actually on this earth somewhere. Maybe you have built yourself an observatory, a big flat circle, carefully marked, maybe with some structures above it, with some metallic frame that allow you to measure where things are at various times, and you can kind of see all the way around. So then part of your story is that this is the horizon. So if you are maybe here, then let's put yourself as being on top of the earth. All right. Then there's a horizon. So that's another circle that's important. The actual horizon of where you are, what you actually see. And we can see some of the complexity that these people were faced with, because at the very least, we're talking about the geometry of a sphere with three great circles. Well, this is not supposed to be anything like that. So here's a great circle. You imagine three great circles representing these three conceptual lines, and then you want to understand what's going on in terms of that system. So, for example, you might want to have coordinates. Let's say here's a star that you're interested in. Okay, so you want to give coordinates to that star. One way of doing that would be to measure how far down you are to the equator, and how far over you are to this point here. This point here is sometimes written as maybe the V. This is corresponds to vernal equinox. So the place where the equator of the celestial sphere's rotation crosses the ecliptic. These are two of these, is one on this side and one on the other side. These are the equinoxes. These are the sort of times when there's as much sun in the day and at night. And there's a natural reference point. So the natural thing to do would be to measure along this direction. These called alpha, and this one here, delta. So these would be called equatorial coordinates, where alpha is called the right ascension. And because it's measured on the equator, it would be measured in hours. So 0 to 24 hours from the equinox date. And delta would be the declination. So how far above the equator or the equator of the celestial sphere star was. And these were the things. So we're typically measuring in angles here. The angles are the natural thing because of the rotation being uniform. And basically, without only established their angular system, that's been basically used by astronomers since then, even in the Western world. Now, I remind you that this is how we can get from addition to multiplication. You replace the circle cross with addition, and then the circle cross prime becomes multiplication. So the successor of addition is multiplication, and the successor of multiplication is exponentiation. The successor of exponentiation is the triangle power, and the successor of the triangle power is the square power. And more generally, in this sort of sequence, that's sort of how we define the higher and higher hyperoperation, that the successor of star k is star k plus 1. So that's how we continue this sequence of hyperoperations, getting more and more complicated ones. So we get here to the next one, star 5. We would just apply this inductive recursive kind of definition. As an example, I remind you that m triangle n is this combination here, m to the m, all the way up to the m, where there are altogether n of these m's. And this operation figured prominently in our discussion of complexity, but we were talking about the minimal way of representing a given natural number, the sum, fixed range of arithmetic operations. What about m squared n goes up 1 from here? Well, let me remind you, we've talked about this before, but it's useful just to be reminded that m squared 1 is m, definition, and m squared 2 is that m triangle m squared 1. M squared 1 is m, so we're talking about m triangle m, which is the tower of m's. This is now m of them. So that's what m squared 2 is a tower of m's where there are m in a tower. And then m squared 3 will be m triangle of this m squared 2 that we just figured out. So m triangle this. And that means there's a row tower of m's where there are altogether this number of m's in the tower. So we can write that as here's the tower of m, and the number in this tower is this number here. So we're getting sort of more and more brackets as we up this second entry in the square operation. So in exercise, you convince yourself that m squared 4 has this expression. Involves 4 towers of m, where this last tower has a single m, and then sort of 4 towers of m, and each one controls the size of the previous tower. In this tower there's m's, in this tower there's that many m's, and in this tower there's that many m's. So it should be now sort of clear that to get m squared 5, you would just extend this diagram by adding yet another bracket, another tower of m's there. So there'd be 5 such towers of m's and so on. And so generalizing, if we're interested in m squared n, then we'll have a picture like this, where there are altogether n towers of m's. 1, 2, that's the nth tower there. So we have a pretty good picture of the square operation. What about the next one, the star 5 operation? Well, m star 5 of 1 is m, and that has to be, and then the definition m star 5 of n plus 1 will be m squared, m star 5 of n. So let's have a look at what happens here with this star 5 operation. So m star 5 2 is by definition m squared, m star 5 1. Well, this by definition is m, so we're talking about m squared m. So that's just like this, but now where the number of towers in this towers is in fact m itself. It's m squared m, equals m squared n. So this thing here is m star 5 2. And then the next one, m star 5 3, will be m squared of what we just got, m star 5 2. So m squared something is a pattern like this where we have towers of m that are altogether n of them. So if we have this number of them, it means we have to have the number of towers here being the same that we just obtained in the previous slide. So we have this row, and the number in this row, the number of towers in this row is given by this quantity here, which is a similar expression with m towers in this one. So here's an exercise. See if you agree with my assessment of what m star 6 is. So here is something like this, looking at towers of m, and then there's a number of races, and altogether now the number of races here is controlled by a similar tower of things, and that's controlled by another tower. So altogether they're going to be similar to the tower, and the final one has m races here. And how many are there altogether in these towers? We found the first one, and the second one, and that m is the nth one. So there's n of them, then we're getting m star 6 of m. So convince yourself that's what it looks like. And then should be somewhat clear how the pattern proceeds. We're going from brackets in this direction, to braces in this direction, to brackets in this direction, to braces in this direction, to brackets in this direction, to braces in that direction, and so on, as we up these subscripts for the operations themselves. So we now have a hierarchy of actual operations, of arithmetical operations. And we have a pretty good sense of how to, at least in principle, write down what any one of these operations does on natural numbers. This sequence of operations allows us to overwhelm any given sequence of bigger numbers. So there's a little bit of upmanship in this game where people try to create bigger and bigger numbers. So sort of a fun game, it's pretty frivolous. But so suppose we come along with a sequence of bigger and bigger numbers. Let's call them sigma 1, sigma 2, sigma 3. And these numbers grow very, very dramatically. That's claims more faster than any previous sequence of numbers. So you can go beyond that particular sequence by creating this particular sequence. 10 star sigma 1, sigma 1. 10 star sigma 2, sigma 2. 10 star sigma 3, sigma 3, and so on. So you can take whatever sequence of numbers they have created and create a new sequence of numbers where you're employing their numbers as not just exponents but also as subscripts of our arithmetical operations. So this will guarantee that this sequence here is phenomenally bigger than whatever given sequence you got. So there's no end to the possibilities for creating bigger sequences. But more importantly, this trick suggests actually a new kind of operation. It suggests some kind of limiting operation, which we might call star infinity. So we're going to go beyond this already very daunting sequence of operations to get at a new one called star infinity. And we'll also have a more sort of finite looking name for it. We'll also end up calling star n. We'll use the letter n there. But at first, let me put this one here because it's more suggestive of what we're going to do. So let's introduce the idea of a diagonal limit. And let's start by considering powers of multiples of some natural number m. So if we look at our first multiplication operator, just ordinary multiplication, m times 1, m times 2, m times 3, m times 4, so be a relatively modest row. m, 2, m, 3, m, 4, m, 5, m, and so on. And then along the second row, we have all the star 2 powers of m. The star 2 is the exponentiation operator. So this is m to the 1, m squared, m cubed, m to the 4. So in the second row, the numbers are increasing faster than they were in the first row. In the third row, we have the star 3 operator, the triangle operator. M triangle 1, that was just M. M triangle 2, that's M to the M. M triangle 3, that's M to the M to the M. M triangle 4, etc. And we can carry on, so M star 1 is a square operator. You get M square 1, M square 2, M square 3, M square 4. And picture those are very interesting. And of course we can carry on with more well higher exponent schema operators. Let's look at this two-dimensional grid of sort of powers of M. And we're going to sit down and just looking at the diagonal. Okay, so two-dimensional grid, like it has a sort of canonical diagonal, so an important object inside. Okay, and if we go down this diagonal, what we see is that the second numbers are increasing by 1, but also the subscripts here are increasing by 1. In other words, we're getting bigger and bigger operators. Each operator is the successor of the previous one. So the operators and the second exponent are marching together as we go down this diagonal. So looking down the diagonal gives us the sequence M star 1, 1, M star 2, 2, M star 3, 3, M star 4, 4. And it's this that motivates this new kind of operator. So we're going to find a new operator called star infinity, which is really encoding this thing here. It's a sequence involving all of these operators, star 1, star 2, star 3, and so on. So here's the definition. The M star infinity, K, is M star K, K. So new definition of new operator between natural numbers. And the idea is to take this second exponent and use it as both an exponent, but also as picking out the particular operation that we're going to use. So this K determines the operator as well as the exponent. And you might wonder why I'm using K here and not our usual N. And the reason is because I want to sort of change notation and replace the star infinity with something more modest looking, maybe star N. But in this picture, the N is actually a fixed letter, a little letter N. And we don't then want to confuse that fixed letter N with the variable that we're using in equations like this. So this is some kind of limiting operator created from the sequence of operators that we have. And the sequence of operators, let's go move down the diagonal to create this new operator, which is star infinity. So we're going to regard this new operation, star infinity, as some kind of limit of the given operation, star 1, star 2, star 3. And we'll write something like this. We'll write this operation, of 3 dots, and an arrow, and then star infinity. So this is a notation that we'll use to represent the fact that this operation is created from the sequence of operations by this diagonal kind of definition. In fact, we'll actually use that terminology sometimes. It's the S infinity is the diagonal limit of star 1, star 2, star 3, and so on. Alright, so we are using words like sequence and limit here, but you shouldn't pay too much attention to that. The critical thing is actually just the definition of star infinity. We don't really need these words to describe it. These words are subjective to give us an idea of what's going on, but in fact they're not very essential. The essential thing is just a formula that tells us how to multiply two things using this particular operation as completely finite involving just these previous ones. Now, I want to, as I said, introduce an alternate notation, and you'll see why in the next video. So let's call star infinity rather star n. Okay, so let's have some examples. So 10 star n 1. Okay, so by definition that's 10 star 1, 1. This 1 here ends up being the subscript of the star as well as the exponent. And so that's 10 times 1, which is 10. 10 star n 2, well that's 10 star 2, 2, to make that exponent appear here and here. Star 2 is the exponentiation operation, so it's 10 squared, which is 100. 10 star n 3 would be 10 star 3, 3, so that's 10 triangle 3, and that's 10 to the 10 to the 10. So we're going reasonably rapidly here, not such a big jump from here, but quite a big jump from there to there. What happens if we keep going? Well, 10 star n 4 is 10 star 4, and the star 4 is our square operation, so 10 squared 4, and that's 10 squared 4 there. So the power again is where the number is power is that. Power is given by this, number of this power is given by this, number of this power is given by this, and number of powers here is 10. So 1, 2, 3, 4, 5 levels. So the next slide you might like to write down expression for 10 star n 6. So what we're seeing here is that this star n operation has a quite different character in some ways from the ordinary star 1, star 2, star 3 operations. That as we're jacking up the second exponent, the numbers are growing much faster than they were for any one of the star 1, star 2, star 3, and so on. So this new operation really transcends in a big way the individual operations, star 1, star 2, star 3, so that we can consider even those these are big operations. So now we have something which is on a much higher level than we had previously. Alright, so this is actually somewhat interesting that purely as a theoretical exercise, we're now in this actually to see moving ahead of something even bigger. Okay, this is really just the beginnings of what we might call the successor limit hierarchy, which is an interesting pattern that's not just connected with bigger and bigger numbers in this somewhat formal scheme, but actually connects with other things as well, and in fact has a basis in the theory of ordinal numbers in modern set theory, which from my point of view is highly problematic, but we'll see nevertheless that there are aspects of that that can be thought about and realized in a rather concrete way, perhaps independent of the usual set theoretical infinite foundation on which we invest. So it's interesting that we can get some kind of ordinal arithmetic here in a non-set theoretical fashion. So that's what we'll do in our next video. I'll go over that. I'm going to walk over address this very key problem of infinity in mathematics, which supposedly plays a big role, but actually doesn't really logically work. So it's time for us to think again, spell infinity from mathematics, return mathematics to a more modest, sensible, logical enterprise the way it used to be before the 20th century fantasy